the James Webb Space Telescope, the most advanced observational tool ever deployed by humanity, recently uncovered a breathtaking celestial event that has sparked intense interest and speculation throughout the scientific world, far beyond the familiar glow of the Moon and the orbits of Mars and Jupiter. Out at the frigid frontier of our solar system, an immense object collided with Neptune. For the first time in recorded history, a space-based observatory has captured the unmistakable traces of a massive impact on the surface of one of our solar system's distant gas giants. This discovery extends far beyond the boundaries of Neptune, prompting a fresh look at the dynamic and often violent processes that govern planetary systems. The event first came to light through an unexpected anomaly. During a scheduled observation aimed at monitoring Neptune's atmospheric patterns, part of a long-term study of its seasonal variations, the James Webb Space Telescope picked up some surprising data. Bright spots appeared where typically the planet's smooth bands of methane-rich clouds swirl quietly. Instead, chaotic patterns and localized heat surges disrupted the planet's visual and thermal profile. Webb's infrared sensors identified intense spikes in temperature concentrated around a particular region of Neptune's atmosphere. These were not minor irregularities. The magnitude of these anomalies suggested a vast release of energy, one that could only be explained by a major cosmic collision. Thanks to the telescope's extraordinary resolution, researchers were able to quickly reconstruct the event. A large object, potentially a rogue asteroid or a small displaced dwarf planet, had slammed directly into Neptune. Infrared analysis indicated the intruding body may have been several tens of kilometers wide, barreling toward Neptune at incomprehensible speeds. The force of such a collision would release energy rivaling the combined might of the world's nuclear arsenals millions of times over. The impact penetrated Neptune's upper atmosphere, briefly disturbing the planet's deep, multi-layered weather system and generating shock waves that rippled through its delicate cloud structures. This was far more than just space debris brushing against a planet. It was a cosmic performance of cause and consequence, altering Neptune's atmospheric makeup and revealing processes hidden deep within its mysterious interior. The upheaval lifted materials from Neptune's lower atmosphere into view substances, normally cloaked beneath thick cloud layers, offering a rare opportunity to analyze the planet's chemistry, which until now had largely remained theoretical. Beyond the spectacle of the impact, the incident raised critical questions about the stability of the outer solar system. It was long believed that Neptune and Uranus orbited in a relatively undisturbed environment, changing slowly over millennia. But this unexpected event suggests that even at the solar system's coldest edges, massive and dramatic events still occur. Webb's observation implies that the Kuiper Belt's sprawling region of icy remnants beyond Neptune may be far more active and volatile than previously thought. The idea that large bodies can be ejected from this region and hurled inward introduces a host of implications for planetary safety and the long-term evolution of the solar system. The immense size of the impactor suggests that gravitational influences, perhaps from unknown massive objects lurking beyond Neptune, like the hypothesized Planet 9, or even nearby rogue stars, may sometimes destabilize the orbits of Kuiper Belt objects, sending them inward on destructive paths. If such disruptions happen more frequently than once assumed, it suggests that all planets, including Earth, may occasionally face the threat of catastrophic impacts from deep space, though on very different timelines. Neptune's magnetic field, one of the most peculiar in the solar system due to its severe tilt and offset center, may also have been temporarily influenced. Preliminary data following the collision showed disturbances in its magnetic field, opening a new line of investigation into how external forces can influence magnetospheres, a key factor in assessing planetary habitability, particularly for distant exo. Additionally, this event invites a re-evaluation of the long-term geological and atmospheric development of ice giants. If such immense impacts happen even once every few million years, they could significantly influence a planet's atmospheric chemistry, internal heat distribution, and even its spin. Features observed on Neptune or Uranus once thought to be slow, naturally evolving characteristics might actually be scars left by ancient, violent events like this one. Webb's ability to detect this collision and monitor its immediate effects with unparalleled clarity marks a breakthrough in space observation. Earlier telescopes may have missed this entirely or only recorded faint remnants. Webb's sensitivity enabled scientists to trace thermal and chemical shifts in real time, map the dispersal of ejected material, and model how energy ripples through Neptune's dense atmosphere. This dramatic event also reignited a deeper awareness of cosmic vulnerability. Despite all of humanity's technological progress, this sudden act of planetary violence on a remote world reminds us that space is still a realm of unpredictability and change. The same forces that forged our solar system random impacts, gravitational instability, and massive upheaval continue to operate. Earth's relative peace may be a temporary and fragile gift. It's not a permanent state. This realization underscores the urgency of studying planetary impacts and, perhaps one day, preparing to shield our world from similar threats on a broader philosophical level. Events like Neptune's impact remind us that planets, stars, and entire systems are not static. They are ever-shifting participants in an ongoing cosmic story. Worlds can be shattered, atmospheres stripped away, and orbits radically altered. The Neptune collision shows that even the most majestic planets are vulnerable to transformation in an instant. Influenced by forces vastly older and more powerful than ourselves, in the wake of this discovery, the scientific community stands at the threshold of a new age of understanding. Fueled by Webb's capabilities and driven by the mysteries this event unveiled, researchers are diving into countless simulations, debates, and studies to unravel what occurred. How often such collisions take place, and what this means for the architecture of the solar system. Questions about the impactor's origin, its composition, and its path through space will guide research for years to come. Initial simulations suggest that the object likely shattered upon impact, descending high speed, fragments deep into Neptune's interior. If true, the planet's internal structure may have been subtly but measurably changed. Every layer of Neptune atmospheric, magnetic, and structural may now carry evidence of this brief but profound event, encoding its story for future generations. Of astronomers to decode observations of the resulting debris cloud provided a unique opportunity to examine how Neptune's atmosphere responds under extreme conditions. The expanding shockwave revealed complex atmospheric motions refining existing models of gas behavior under such cold and high-pressure environments. This not only deepens our understanding of Neptune itself, but also informs how we interpret similar features on distant exoplanets. One of the most intriguing implications is that events like this might explain the long-standing mystery of Neptune's heat output. For decades, scientists have puzzled over why Neptune emits more heat than it receives from the sun. Perhaps occasional high-energy impacts like this one contribute to the planet's internal heat, injecting energy and disturbing its thermal balance in significant ways. Instead of a slow, consistent cooling process, Neptune's internal energy may be sustained by these rare but potent bursts. For planetary scientists, this was a rare and invaluable chance to witness the chain reaction of a massive cosmic impact. In real conditions, the knowledge gained will ripple through many disciplines. From modeling how planetary systems form, to understanding atmospheric chemistry and preparing for the possibility of future Earthbound threats, the collision on Neptune becomes a case study in how destruction and creation coexist in the universe's design. While Webb has already transformed our view of space, capturing this event highlights something even more remarkable: our ability to witness the solar system's raw and unpredictable energy as it unfolds. As more data flows in, each new detail adds depth to the dramatic and evolving portrait of Neptune, not as a quiet outpost, but as a stage for celestial upheaval. This moment reaffirms a fundamental truth. The universe is not a static sculpture, but a living, evolving entity, forever reshaping itself through gravitational dance, sudden collisions, and chaotic transformation. Neptune's recent upheaval revealed by Webb's unblinking gaze, is not an isolated occurrence but part of a greater cosmic saga stretching from the birth of our solar system into a future still unwritten. Though the planets may seem serene from afar, up close, the universe tells a story of motion, fire, and chance. And this newest chapter, ept in Neptune's stormy blue clouds, is a monumental reminder of the cosmos's restless, creative heart as high-resolution data continued to arrive. Scientists realized the effects of the impact might reach Neptune's complex system of moons and rings. Initial observations indicated the collision may have subtly altered the orbits of inner moons, like Naiad and Thalassa,